At its heart, machine learning aims to find a function that maps input data to output results, like y equals f of x, where x represents the input features and y the output prediction. But there's a lot of ways to do this. For instance, if you have data about customers' purchase histories, x, and want to predict how much they'll spend next month, y, finding the function of f means adjusting model parameters so that it accurately links purchase histories to spending amounts. In supervised learning, the process resembles having a collection of labeled recipe cards. Each example comes with both the ingredients and the final dish. The model learns by associating features with their correct labels. You can think of the problem as finding the best parameters that minimize the overall prediction error across all examples. For example, when classifying emails as spam or not spam, the model systematically reduces its mistakes by tweaking its internal settings until its predictions align closely with the given labels. Here, L represents the loss function that measures the error between the predicted and true labels. Unsupervised learning takes a different approach by dealing with data that has no labels. The objective is to uncover hidden parts or natural groupings within the data. Instead of minimizing a loss function based on known answers, the algorithm optimizes an internal criterion that measures how well the data is structured. This might involve grouping news articles into themes or finding latent topics in customer reviews. The important part here is that the model extracts the structure without external guidance. Here, Q might represent a measure of cluster cohesion or data likelihood. One of the most powerful techniques is linear regression, which predicts a continuous output by assuming that the outcome is a weighted sum of the input features. For instance, if you wish to estimate someone's monthly electricity bill, you would consider factors like the size of their home, number of occupants, and average outside temperature. In this scenario, the prediction is the sum of an intercept and a series of products between each feature and its corresponding weight. To determine these weights, the model minimizes the mean squared error, the average squared difference between the actual values and the predictions, often solved by either a direct algebraic method or an iterative optimization algorithm. The coefficients bj are determined by minimizing the mean squared error between predictions and the actual values. When the goal shifts to classification rather than predicting a continuous number, logistic regression comes into play. This method is designed for binary outcomes, such as determining whether a transaction is fraudulent or legitimate. Instead of directly predicting an outcome, logistic regression computes a weighted sum of the features, similar to linear regression, and then applies the sigmoid function to transform this sum into a probability value between 0 and 1. The model is trained by adjusting its parameters to minimize the difference between the predicted probabilities and the actual binary labels, typically using a loss function called cross-entropy or log loss. Here, P is the probability of the event, e.g. fraud, and the model is trained by minimizing cross-entropy loss. K nearest neighbors offers an alternative approach by foregoing an explicit mathematical model in favor of a more direct, memory-based method. Instead of calculating coefficients, KNN simply stores all training examples. When a new data point appears, the algorithm finds the K most similar examples using a distance metric like the Euclidean distance and bases its prediction on these neighbors. For instance, if you want to predict the price of a new house, KNN would identify houses similar in size, location, and other attributes, and then average their prices. While this method is intuitive and often effective for local predictions, it can become computationally intensive as the dataset grows. The underlying math is minimal, essentially a distance calculation and an averaging operation, but the key is that KNN embodies the idea of using nearby examples to guide predictions. This minimal formula encapsulates the idea of using the average of nearby examples to predict a new value. Support vector machines take a more geometric perspective on classification. Imagine you have two groups of data points, such as different types of flowers, and you want to draw a line or a hyperplane in higher dimensions that best separates these groups. SVM does this by not only finding any separating line, but one that maximizes the distance, or margin, between the closest points of each group. The optimization problem is formulated to minimize the squared norm of the weight vector while ensuring that every data point lies on the correct side of the margin. If the data are not linearly separable, the model can project them into a higher dimensional space using a kernel function, allowing for more flexible decision boundaries. Although the underlying optimization involves quadratic programming, the essential concept remains clear. Find the boundary that best separates the classes with the largest possible gap. This equation ensures that the margin is maximized while each data point is correctly classified. Speaking of, thanks so much for all the support on the channel lately. It really means a lot, and I want to give something back to you guys. So do you need a job? That sounded a bit weird. But whether you're a UX designer, app developer, freelancer, or just a curious viewer, I want to get to know you guys, share some UX and UI tips, and maybe even get a gig. So I made a Discord channel for us and want to make this the place to be for front-end professionals. And I'm having talks with people to get some employers in there so you can connect with them too and find some jobs in the future. I'm really excited to get this thing started, so I hope you'll join me. Naive Bayes applies the principles of probability to classification by leveraging Bayes' theorem. The classifier assumes that the features are conditionally independent given the class label, a simplifying assumption that makes the mathematics much more tractable. For example, in spam detection, the model calculates the probability that an email is spam by multiplying the individual probabilities of each word appearing in a spam email and then adjusting by the overall probability of spam. Despite its simplicity, this method can be highly effective for many classification tasks. Decision trees build a model by making a series of decisions, much like a flowchart. At each node in the tree, the algorithm decides on a question to ask about the data, such as whether a particular feature exceeds a certain threshold. The aim is to choose splits that result in the most homogeneous branches, thereby reducing the impurity. The process of measuring an impurity and deciding the best split involves calculating the difference between the impurity of the parent node and the weighted impurities of the child nodes. While the calculation itself might involve measures like Gini impurity or entropy, the overall idea is straightforward. Ask questions that best separate the data until you can make a clear prediction at the leaves of the tree. This formula quantifies how much a particular split improves the homogeneity of the child nodes. Ensemble methods improve predictive performance by combining the outputs of several models. The idea is analogous to seeking multiple opinions rather than relying on a single expert. By averaging the predictions or taking a majority vote among several base learners, ensembles often reduce errors that individual models might make. This simple averaging helps reduce the variance of individual models' predictions. Bagging, or bootstrap aggregation, is a specific type of ensemble method where multiple models are trained on different random subsets of the data. Each model, such as a decision tree, learns from its own bootstrapped sample, and the final prediction is the average of these individual predictions. Random forests extends this idea by introducing further randomness at the feature level during each split in a tree, thus producing a collection of diverse trees whose aggregated output is more robust than any single tree. The fundamental mathematics of bagging involves simple averaging, but its strength lies in the statistical principle that combining diverse models reduces overall prediction variance. This method reduces overfitting by averaging across diverse models. Boosting models build a strong model by sequentially adding weak learners, each one focusing on correcting the mistakes of its predecessors. A common approach, known as gradient boosting, updates the model by adding a new weak learner that approximates the residual errors from the previous iteration. The idea is to adjust the prediction gradually, using a learning rate to control how much each new learner contributes. Although the sequential updates and gradient computations add layers of complexity, the underlying formula is kept minimal by focusing on the additive nature of the model. This process gradually shifts the model toward a more accurate prediction by continuously correcting errors. Here, Fm-1 is the current ensemble, Hm is the new weak learner, and V is the learning rate that regulates the update size. Neural networks are inspired by the structure of the human brain, consisting of layers of interconnected neurons. Each neuron takes inputs, applies a weighted sum, adds a bias, and passes the result through a nonlinear activation function. A typical layer transformation might be described by the equation activation of the next layer equals the activation function applied to the product of the weight matrix and the current layer's activations plus a bias. Although the internal computations involve matrix multiplications and nonlinear functions, this minimal formulation captures the essence of how information is processed through the network. Training such a network involves backpropagation, where gradients of the loss function, with respect to each weight, are computed and used to update the model. This equation represents the forward pass from one layer to the next, where w to the power of L and b to the power of L are the weights and biases, and delta is the activation function. K-means is a widely used clustering algorithm that partitions data into groups by minimizing the distance between data points and their respective group centers or centroids. The method iterates by assigning each data point to the nearest centroid and then recalculating the centroids as the average of all points in that group. The central mathematical objective is to reduce the total squared distance between points and centroids. Even though this single formula is simple, the iterative process behind it requires careful initialization and convergence checks to avoid suboptimal groupings. This objective ensures that each point is as close as possible to the center of its assigned cluster. When faced with data sets containing many features, reducing the number of dimensions can simplify analysis and visualization while retaining the essential structure. A common linear approach projects the high-dimensional data onto a lower-dimensional subspace using a transformation matrix. While the basic formula is new representation equals the projection matrix times the original data, the underlying process involves finding the optimal subspace that captures the most variance, which can be achieved by methods such as principal component analysis, or PCA. Here, X is the original data, P is the projection matrix, and Z is the reduced representation. PCA is a cornerstone technique for dimensionality reduction that finds the directions of maximum variance in the data. Its core operation involves computing the covariance matrix of the data and then solving an eigen-decomposition problem. In simple terms, you seek eigenvectors that, when multiplied by the covariance matrix, yield the same eigenvectors scaled by corresponding eigenvalues. These eigenvectors form the new axes for the data, and selecting the ones with the highest eigenvalues allows you to retain the most significant patterns while discarding noise. This eigen-decomposition reveals the principal components, eigenvectors v, and the amount of variance they capture, eigenvalues lambda, allowing you to retain the most informative directions.